Okay, so on the horizon of entanglement-assisted communication networks is a quantum internet, which will be a parallel infrastructure for parallel to the classical internet that will hopefully be able to transmit quantum information to anywhere in the world. That's of course an ambitious plan, and to realize that will require solving novel design challenges at every layer of the technological stack. So from the physical layer of quantum devices through to the classical control plane above that layer, up to user applications. And just as for classical networking, we can expect that simulation will be critical for guiding these developments. So what's involved in simulating a quantum internet? A key consideration here is the physical non-idealities of the network, which in fact the key resource involved in the quantum internet, and particularly its performance in terms of its rate and its fidelity. So these non-idealities can cause loss of qubits and photons, which affect the rate, and cause noise in processes on devices and in quantum memories that affect the quality or fidelity. Now, there are methods to mitigate these effects. So noise can be dealt with, for instance, with entanglement distillation. So if you can make multiple copies of your entanglement, then you can distill it probabilistically into a higher quality or higher fidelity entanglement pair. And to deal with loss, especially in channels, where the loss in fiber, for instance, is exponential, this can be mitigated by placing quantum repeaters in between the channel to essentially shorten the lengths on both sides, establish entanglement first on both of those arms, and then perform what's called an entanglement swap. Now, the challenge with both these methods is that they're generally probabilistic. And if you also were to combine these two, you see that, for instance, in the quantum repeater case, if you're waiting on both of those entanglements to reach a certain quality, for instance, through distillation, one may succeed much earlier than the other, and therefore the qubits involved on one arm will be waiting and decohering. So there's a complex interplay here of timing effects that are also related to modeling this physics accurately. So these are two important considerations. Another, of course, is if the ambition is to go to a quantum internet, is that the simulator should be able to scale to large networks and thereby also be able to simulate large quantum states. And then thirdly, it's important that the simulator is versatile, so that it's not really an ad hoc simulator geared towards one type of platform, but that it can be used to compare and benchmark different hardware platforms, for instance, nitrogen vacancy centers versus trapped ions, or potentially even look at hybrid interfaces of such devices. So those were three requirements we considered important at QTech several years ago for simulating a quantum internet, and we couldn't find existing tooling to help us with that. So we began developing our own simulator that we called NetSquid. So that's been under development now for, well, close to 4 years. And we publicly released it last year in a beta release in the summer, and then version 1.0 in close to Christmas. So NetSquid, well, it's short for the Network Simulator for Quantum Information using Discrete Events. It's essentially a design tool for scalable quantum networks, but potentially also for modular quantum computing, where a lot of the same considerations enter. Its key features are that it uses a discrete event simulation engine. I'll say more about that in a second. So that deals with the requirement of timing accuracy. It has a specialized quantum computation library that helps with its scalability, and a modular component library that helps with the versatility. The use cases essentially range also across the quantum network stack, from exploring requirements of the physical layer, to designing control protocols, to analyzing the feasibility of user applications. If we take a look inside NetSquid, a look inside. Firstly, it's a Python package. Under the hood, it does use more performant languages for sort of performant parts of the code. And here you see the sort of the architecture of the package. It's made out of several sub-packages, and actually it depends on a separate package also developed at QTech, which is the discrete-event simulation engine PyDyna. It has a sub-package for the specialized computation with modular component library, and then also at the top this framework for modeling the classical logic that we refer to as protocols. Zooming in a bit on the discrete-event simulation engine. So this is a paradigm for simulating networks adopted from classical network simulators, where it's used a lot. This type of simulation can deal very well with the stochastic processes in quantum networks. Here you see a short example of how it would work for quantum teleportation. Essentially, rather than stepping continuously through time, the engine jumps from event to event in its future timeline. And as it jumps to an event, it checks if there's any entities in the simulation that care to react to that event. And if so, these entities can then run their code and potentially schedule future events and future handlers of events. So it's a bit like reading a comic book, if you will. So you see you generate entanglement in the case of teleportation. Alice will measure and send, Bob will store and wait, and eventually Bob will apply corrections. The other interesting thing here is that the quantum information is essentially dormant until it's accessed during an event. And then we will retroactively evolve it to account for any noise processes that may have experienced. Also at the bottom of this stack is what we call qubit subpackage. So in NetSquid, qubits are the actors in the network. So they fly around or they sit in memories, and they dynamically share their quantum states. And they do so internally. So this is done automatically. So you don't have to manage your own quantum states. NetSquid will dynamically track which qubits are entangled with each other, which ones share a quantum state. We'll combine those states as those qubits interact, as you see in this example to the right of a distillation process. And then as you measure, it will again split the qubits off and end with a smaller state. So this is important for keeping quantum states as small as possible. So you can have many different quantum states or registers in your simulation at one time. It also offers a seamless choice of quantum state representations for these states. So I say seamless because essentially you switch on which one you want to use, but you don't have to change anything else in your simulation of how you deal with qubits. Here you see 4 of the representations on offer. So ket vector, density matrix, stabilizer state, and graph states with local Cliffords. And these have trade-offs in terms of their universality, how versatile they are for modeling noise, but at the same time, how they scale in terms of memory usage and computation speed. So for instance, the stabilizer states are limited to Clifford gates, so they can only model a subset of noise and processes. So we're not universal in the quantum computing sense, but they scale much better in terms of memory and computation usage. So depending on how large your network is and the detail to which you want to model, you can make a choice here of which representation to use. Then we have what we call the component library. So this provides a selection of base components that you can use to build up your network. So think of channels, classical channels, quantum channels, memories, detectors, quantum processors. And these can then be composed inside other components. So here you see a simple example of heralded entanglement generation. between two nodes where there's a quantum channel, which internally, sorry, a quantum connection, which internally consists of channels and a Bell state measurement detector. And these components are then linked together with ports to pass classical or quantum messages. And this example of, sorry, let me first add, so that's the component part. The components themselves are composable of physical models. For instance, delay models, loss models, different kinds of gate errors that essentially define their physical characteristics. So you can take a base component like the quantum processor, and then by how you essentially define the topology of the quantum memories and the gates between them and the different models, you can model an NV center or a trapped ion. And then last, there's the protocols subpackage, providing essentially the classical control over your simulation. Here you see a sort of a simple example of essentially two nodes playing ping pong with a qubit, and how you would represent that in NetSquid as a protocol that you could assign to each node, where there's an asynchronous feature to yield on something happening. So in this case, both protocols will yield on some input on their port. When they receive it, they will measure the qubit, in this case, in one of two different bases, print that result, and then put the qubit back on the port. So the important thing about protocols is that essentially allow you to describe local behavior in an asynchronous way on different nodes. So to put all that together, here's an illustrative example of how a quantum repeater could be simulated in NetSquid. So the first step would be to model the network setup using the components. So very similar to what I just showed with quantum connection. In this case, there's a source in the middle and the processor. The second step would then be to assign protocols to those nodes. So for instance, each node has a protocol to allow to generate entanglement with its neighbor. There's also a protocol to perform entanglement distillation in this case, and the middle node has a protocol to do an entanglement swap. Once that is set up, you can then essentially push play, and the discrete event simulation will step through the different events where entanglement is generated, where distillation is attempted. In the bottom here, you see that distillation fails, and therefore the process has to repeat. These little blue circles here are qubits, and this is illustratively showing the entanglement between them, the quality. And as you see, because this qubit, the qubits in nodes A and the repeater node have had to sit in memory while this bottom arm of the repeater is still trying to distill, the fidelity worsens, and eventually when the swap happens, it's not a perfect quality entanglement. Then lastly, that's one run, and essentially independent of whether you're using mixed states, density matrices, or pure states, when a measurement is performed in NetSquid, we roll the dice and we will just choose one outcome, because classical decisions in the network can be based on that outcome. And in that sense, one simulation run will follow a single quantum path through a quantum phase space, if you will. And to be able to analyze the performance of your network setup, if you're not emulating, but you're simulating, then you will repeat these runs n times and take a statistical analysis of the results. For instance, to have a metric such as an average fidelity of your network or the average rate. So that's how NetSquid works. So then I will go over a few use cases. So co-author on our NetSquid paper, Tim, worked on simulating a quantum switch beyond its analytically known regime. So this switch essentially sets up GHZ states between the nodes it's connected to. There was a paper essentially analyzing this with Markov chains, I believe, by Guy and Varian, And it's in an upper bound in the case of 4 partite states. And Tim showed that using NetSquid, he could go beyond this bound and actually calculate the capacity in this case, and also add time-dependent noise, which also seems analytically intractable for this example. He also worked to do a hardware parameter sensitivity analysis using NetSquid for an NV repeater chain to study for NV centers to compare near-term to sort of far-term hardware quality. So that's another use case. Also, 2 co-authors, David and Julian, use NetSquid to compare the performance of 2 different types of atomic ensemble quantum memories, which also showcased the modularity of NetSquid, and that they could keep the network set up the same and really just change the models of these memories, and in that way run this comparison. Where I believe one is more efficient and the other one uses multiplexing. That project was also part of the Quantum Internet Alliance, which has a broader goal of developing a blueprint for pan-European quantum internet. And here NetSquid is being used sort of at different levels of optimizing this blueprint, both in terms of protocol design and the node placement for repeater architectures. And another example of that is EuroQCI, where NetSquid was used last year for an upgradability study to see how near-term QKD network architectures could be upgraded to entanglement-based quantum information architectures. Then lastly, going up the stack a little bit, NetSquid has been used in several cases, both to aid in the design and validation of different quantum network protocols. So it was used for the development of the first link layer protocol for quantum networks, the design of the quantum router architecture, and also in the design of the quantum network protocol. And this is a talk Wojciech will give on Friday morning. So that was the NetSquid use cases. I think I have 2 minutes, so that's, I think, good timing. So how can you get started with NetSquid, which I hope I've motivated you to do? Well, if you visit the website, you can register on our user forum. So by registering, you agree to the end user license we have, which is free for academic use. And that registration then gives you access to installing it using just this Python package manager pip. So it's just one command where you have to fill in your credentials, and also to the online documentation where there's user tutorials and a 10-minute guide on how to get started. Then lastly, we provide essentially a template to users to develop extensions to NetSquid that we call snippets. So these snippets or extensions are created, maintained, and shared by users. We host a selection of them on the website and also on our package server. And we highly encourage anyone to contact us if they have a snippet they would like us to list on that server or on our website. So yeah, the idea here is really that the modeling on top of NetSquid, and there's already a range of examples. For example, there's a snippet for the physical layer or NV, but also for memory managers and so forth. But these are contributed by users. Right, and of course, NetSquid was a team effort over the last, as I said, almost 4 years, involving several people, also the Surf Sarah HPC Institute in the Netherlands. Yeah, so that's it. Thank you.
Thank you very much for the nice talk. Are there any questions?
You should start with the standard question with C2.
Oh, okay. So let's start with the standard question. The first one is, what will be the first use case for entanglement-assisted communication networks?
So, yeah, I'm not sure exactly how that is defined, but assuming any kind of entanglement assistance, then I guess it's device-independent QKD.
Okay, and then on the path of realizing this use case, what is the current main challenge in your field?
I think the challenges in the field are, well, I think maybe so modeling device-independent QKD of NetSquid should already be possible. I think the challenge would be sort of making the community aware that tools like NetSquid exist for these kind of use cases. So I think there's a challenge of sort of dissemination and community growing to get the word out there that these kind of simulation tools are available for use cases like device-independent QKD, but also, of course, use cases beyond that.